let's begin. Let's pick up where we left off. So, want to find the radius of convergence and interval of convergence of this guy. What do we do?
Ratio test.
Ratio test. So by the ratio test. We need, well, we want the limit as n approaches infinity of, I'm going to put this to the n plus 1, over n plus 1 factorial, divided by that, which means multiplying by the reciprocal. Need that to be less than 1. This means this cancels into not all of that, but that, and what does this simplify to?
1 over n plus
1 over n plus 1 times x. Okay, now if I take the limit as n approaches infinity of that, what do I get?
1.
0. What does that mean? So that's the 1, and it's literally less than 1 always. What does that imply?
Converges absolutely.
Yes, but where? What's the radius? What's the interval?
For all real numbers.
Right. This is one for, so this means it converges absolutely for all real x. i.e., the radius of convergence is infinity, and the interval of convergence is from minus infinity to infinity. It converges everywhere, absolutely. This is actually an important power series. We will see that in a little bit. Yeah, this one has an infinite radius of convergence. Converges everywhere. Because this is actually always less than 1, regardless of x. I didn't even have anything to solve for to get an x. Find what x's make it work. It'll always work. 0 is always less than 1. Now, let's move on to another important topic. Talk about representing powers, representing functions with power series. Last time we saw that if I look at this series and it goes from 0 to infinity of x to the n, I could actually think of that as the function 1 over 1 minus x because it was geometric with a equals 1, r equals x. And so this is on the interval x strictly less than 1. It diverged both at positive and negative 1. We showed that last time. So as long as I'm on the window minus 1 to 1, not including the endpoints, I can think of this function as this series. Moreover, it's geometric, and we also did the ratio test for this yesterday, I believe. So we actually know that this convergence, this guy converges to that function absolutely, as long as I'm in this interval. Now, there are some immediate consequences of this. This is important because things like something I mentioned in passing, the rearrangement theorem. Basically tells us this guy is going to be expressed as this infinite sum in such a way that if I were to manipulate the terms in terms of their order, or I want to do any calculations with them, it's not actually going to change the answer. Because if something is conditionally convergent, it turns out that doing that kind of thing can change the answer. However, this allows the absolute convergence here means that the answer won't change once I start doing certain operations on this series. So this means, for example, we can do something called term-by-term calculus. Basically, the idea is, if these guys, this series actually converges to that function, it stands to reason, at least when I'm in this interval, anything I can do with this function, I can do to this series. I can, for example, differentiate this function, and I would be able to differentiate that series. Now, what does it mean to differentiate that series? Well, you imagine that as an infinite sum. I'm just differentiating each term, because that's what the theorem says. I can differentiate each term in a sum. That's one of the properties of a derivative. And you might wonder, well, how do you know that sum makes sense? How do you know, what if once you start differentiating, stuff is going to happen? Maybe if someone wrote this in a different order, you'd get a different derivative, and there's all these issues. None of that matters, because we have absolute convergence. We have absolute convergence. So we can do things like, for example, we can differentiate term by term. I'm not going to go into the theory of why this is all possible. Just know that when you're absolutely convergent, this is all possible. So I can do something like find the derivative of this series. And it will be equal to just differentiating each term. You couldn't do that with a conditionally convergent series. But with an absolutely convergent series, it does work. And I could do something like integrate this series with respect to x. And what is that going to be? Well, I can think of it as the sum of the integral of each term. This is called term-by-term differentiation. This is called term-by-term integration. And these are all possible because of the absolute convergence of the series. Now that's really cool because I can now find series representations for all sorts of functions. Like if I know about the series representation of one function and I know where it converges absolutely, I can talk about series representations for the derivative of that function, the integral of that function, as long as I maintain the same interval where I have absolute convergence. So, using this fact, we can figure out our series representation. For related functions. For example, find a power series for, let's do several examples here. A f of x equals 1 over 3 plus x. B f of x equals 1 over 3 plus x all squared c f of x equals ln of 3 plus x. And where do they converge? So I'm going to use, for example, the fact that I know how to write 1 over 1 minus x as a power series to write other functions as a power series. So let's jump in. A. Anyone see how I can use the previous fact to talk about a power series for this guy? Ideas? So the fact that we know is 1 over 1 minus x, I can write it like this. And for now, think of those as 1 is this and the same. Given that I know that, what do you think I can do with this? Ideas? Thoughts, suggestions? Yeah?
Negative 3x to the n. I don't know, I just like it, I guess.
Well, why would you guess that? Like, what are you trying to do?
I don't know. Like, I was just thinking, like, since it looks the same,
Does it look the same though?
well, like, besides,
Here's a question, could you make it look the same, pretty much?
yes.
How would you do that?
If you factor out a negative 3, or,
Well, factoring out a negative 3 would actually give us 2 negatives, which we only want 1. Yeah, Bria?
If r equals negative x and a equals 3.
R equals negative x and a equals 3. That does what for us?
You can like rearrange the terms so it looks the same. Make it,
Are you trying to think geometric, a over 1 minus r? Is that what you're thinking about?
yeah.
Yeah, but the a would be on top, so that doesn't really fit. But close. But let's just go with the first idea. Can I make this look like that? Or the differences so far? Well, there's a 1 here, and there's a 3 here. How could I legally get a 1 in this position? Yeah. Thinking too complicated. In terms of like basic algebra, yeah.
Just plug in something else instead of x, like negative x minus 2.
Negative x minus 2. How would I do that though, legally?
Just instead of x, so it would be f of negative x minus 2
Okay.
equals 1 over 3 plus negative x minus
So that'll help me find the power series for negative x minus 2 though. F of negative x minus 2. How do I get to the power series for f of x if I did that? Right, because I mean, how do you go from this and get to that?
like let f of x equal, I don't know.
Yeah, so we can't just take something and plug in a random value that we want. Yeah.
Factor out 3 from the bottom, so that's 1 plus x.
Okay, so if you factor out a 3, we would have what? 1 plus x over 3, right? That's completely legal, not changing any values, not rewriting any functions, not plugging in anything anywhere. So I just have the constant 1/3 and this, anything else I can do? Yeah.
Well, now would R just be equal to negative x over 3?
So 1 minus negative x over 3. And yeah, so now I can think of that as a geometric, right?
So A would be 1/3, and R is negative x over 3.
I could have think of A as 1/3 and R as negative x over 3. Now, so this guy here, is kind of in the place of this guy here, and we know for this guy, we needed him to be between plus and minus 1. So that also means for what we're about to do, in order for it to work, I would need this to be between plus or minus 1, right? And what's that going to mean for x? Well, that would mean x would have to be between, say, plus or minus 3, right? So that's the first thing. So where is it going to converge? What I'm about to do, this manipulation is going to work as long as my x is somewhere between minus 3 and 3. That's the first thing. Now, once I do that, this is 1 over 1 minus a variable. This is 1 over 1 minus a variable. It is equal to the series of that variable to the nth power. So all I'm going to write this as is 1/3. And this will work for x strictly between 3 and minus 3. I can actually rewrite this a little bit. So here I would have the sum minus 1 to the n, x to the n over 3 to the n plus 1. So it turns out I can think of the fraction 1 over 3 plus x to be that series, right? Meaning I can actually start plugging in some terms here. So this would be 1/3 minus x over 3 squared plus x squared over 3 cubed minus x cubed over 3 to the 4th plus x 4th over 3 to the 5th minus dot dot dot. If I expand this polynomial going on forever, what would that add up to? This function. Does that formula always work? No. As long as my x is in this range, it'll work. Outside of that window, this series is going to diverge. Because once my x hits something larger than 3, what's going to happen? If I plug in x equals 4 here, now that's like a geometric series with your r would be like 4 over 3. So we know that's going to diverge. So as long as I keep my x within a certain window, this series will actually represent that function. That's the answer, and that's where it works. Okay, what do you think for this one? What kind of manipulation can we do to get that? It's going to be the question. So here, just a little factoring trick, and the same kind of trick that we use when we want to figure out, like if I tell you, oh, the equation of a circle is x plus 1 squared plus y minus 3 squared equals 4, you kind of know to think of this as x minus a minus 1. So if I ask you the center, you know, oh, it's minus 1 comma 3. Right, that same manipulation you did in your head is what we did here. Right, if there's a negative sign and I want to, if I have a positive sign and I want a negative sign, you can always think of the negative of a negative. So, but what trick can I use to get a square in the denominator? ideas on that? You can't just randomly square a denominator, right? There has to be a legal way to actually get that. Yeah.
Could you do like a partial decomposition of the?
Sure, that might give you like an a over 3 plus x, plus you'd still have like a b over 3 plus x squared, right?
Yeah.
Yeah, so,
So,
yeah, so, and chances are you're gonna have something on top of that square. You wouldn't really get into a better situation. So to get a little bit easier. Like 1 over x versus 1 over x squared. Tell me an operation that goes from one to the other. Other than just squaring the denominator, which is gonna be hard to do in this situation, obviously. Because squaring this denominator here is not the same as squaring that denominator here, because this is a sum. I can't actually do that. What else do we know we can get from here to there? Might remind you of something, hopefully. Yeah?
Since the ones in the numerator, can you break them apart into 2, and then factor out 1/3, and then square the entire thing?
Which part? Where are you talking?
Like,
For here?
no,
What's
no,
one?
oh, I meant the original one.
Here? Like what do you want to do?
I mean, you can break it into 2, and have 1 over 3 plus x, and 1 over 3 plus x.
Yeah, well that gets you like here. That's better?
No, I mean separating them into 1 over.
So you write this as 1 over 3 plus x times 3 plus x, and then do what?
Break it into 2, and then pull out the 3.
How would you break it into 2? You can't really break that into 2. I mean, to break that into 2 would be to do a partial fractions. But we already know that the partial fractions, because this is a repeated factor, it'll give you like a over 3 plus x plus b over 3 plus x squared. You'll still end up in this situation. No one, this doesn't ring a bell to anybody?
It's a good derivative, but
If you took the derivative of this, what do you get?
you'd get negative 1 over x squared.
You should have done that hundreds of times in your life by now. That should almost be, okay, I see a 1 over x and a 1 over x squared. Can't square a denominator. Well, the derivative looks like that. Of course, with a negative sign. So, in other words, what I can notice is that this is the negative derivative of this. And guess what? I know an absolutely convergent power series for that guy. Right? So that's going to be equal to negative the derivative of this is going to be negative the derivative of and this works because of absolute convergence. Okay. How do I find the derivative of this expression here? What's the derivative? What's the derivative of this? Derivative with respect to x. And I can bring this negative, there's a negative 1 out here, I can bring it inside and say bump that power up by 1. That's the new power series. One over 3 plus x squared. I can think of this as the series. N goes from 0 to infinity, minus 1 to the n plus 1 of n x to the n minus 1 over 3n plus 1. And this works on minus 33. That's a power series for this. Now I think you guys see the game I'm playing now. How would you do C? I have f of x equals ln of 3 plus x. Find a power series for that guy.
The integral of the first and
Integral. Notice that this is just the integral of 1 over 3 plus x dx. What I know, a convergent, absolute convergent power series for that guy. This was minus 1 to the n, x to the n, over 3 to the n plus 1 dx. Absolute convergence means I can switch these two. Integral. What is that going to look like?
X to the n plus 1 over n plus 1.
That's power series for the ln. X equals to the series minus 1 to the n, x to the n plus 1 over n plus 1, 3 to the n plus 1. And of course this also works on minus 33. Because it's all built up from the same original guy, which only worked on minus 33. So I can integrate and differentiate on that interval and create new power series on that interval. Bonus. There are many ways to actually do this. But using what we've looked at so far, can you actually write ln2 as an infinite sum? What would you do? You see a nice way to write that as an infinite sum? Do you see it? Yes? No? You want to say it? What is it?
I remember we learned it earlier, where, yeah.
Well, we did it earlier where I expressed it as a different infinite sum,
Yeah.
but there's one that since just now we can do it another way. Ask you about ln2. You know about ln of 3 plus x. Yeah?
Is it when x is valued at -1?
You plug in x equals -1. Notice if we plug in x equals -1, which is completely valid, that is between -3 and 3, then part C gives that ln of 2 is going to be equal to the series of -1 to the n, -1 to the n plus 1 over n plus 1 times 3. So you could actually do that. And if you wanted to, you could write out what that is, and you can actually look at an infinite sum that converges to ln2. But yeah, I believe we looked at another one earlier, ln2. And one of the ways in which they could prove that is kind of because of this. They didn't look at the series as a series, they looked at it as another function. Once you can actually do that, thinking of series as representing functions, you can actually evaluate them really elegantly, let's say. Another thing here, did I actually mention that now? Or no? Here's another example. Kind of shows you where we're going. Evaluate this integral now. Go through all the techniques that we've learned this semester, you will not be able to do this integral, right? Nothing's going to work. However, I'd actually like you to find this integral as an infinite series. Where does this converge? Hopefully we're putting together what we just learned to actually attack some weird integral that none of our techniques can actually compute. Ideas? So far, again, the only thing we know is we're going to find a way to know other things that's coming. This. We know that works on -1 to 1 for x. Use that here to figure this out. What do you guys think? Ideas? ideas? That's how I can use that to get to number. So you ready to make this look like that? Yeah?
Is your A equal to x, then your R equal to negative x to the n?
Yeah, you could do that. How are you gonna, how do we actually turn that into a series?
Maybe
So you want it to look like A over 1 minus R. So your A looks like the X, which is just a constant. And a nicer way to actually see exactly what the series will be is to write it something like this. And yeah, you're kind of thinking of this as the A, and over the 1 minus, that's the R. And here we can have just, the A is a constant, so leave it outside the series for the moment. And this will be minus x to the 9th to the n. This will be, well, this is minus 1 to the n. This is x to the 9n from right here. And if I multiply this x in, I get 9n plus 1. Now this will converge absolutely as long as this works for x to the 9th less than 1, just replacing the r in the original, which of course just means it still works on minus 1 to 1. But on that interval, I can switch these two. This would look like minus 1 to the n, x to the 9n plus 1 over, there's no over, dx. Integral of this guy. What's the integral of this guy?
The power rule again, so it's x to the 9n plus 2 over 9n plus 2.
Of course, there's going to be plus a constant. Now it turns out you could actually find out what that constant is, but I think we'll do that next time. But that's what the answer would be as a series. So for example, if you were to, calculators are sophisticated these days, they can figure out what that is if they go into the complex numbers. But maybe an older generation calculator, if you had asked it how to integrate this, it would probably tell you, oh, we can't do it. But if you asked it a definite integral, and you were somewhere in here, then what your calculator would actually do is convert it to a series. It would add up a bunch of terms, and you might notice that this is an alternating series, which means we actually know how to approximate them very well. So your calculator, if your calculator has, 8 digits on the screen or something like that, it can just keep adding up these terms until the very next term would be something where the decimal expansion only has 8 digits. And then it will stop at that point and it'll say, hey, here's your answer. Right, so you'll see that from time to time. If you were to type into Wolfram Alpha, what is the integral of e to the x squared? It'll tell you, oh, you can't do this in elementary functions. Yet if you were to say, okay, what is the integral of e to the x squared from 0 to 1? It'll somehow pop out an answer. And you're like, well, how could you tell me the answer for the definite integral and you couldn't tell me for this? Right? That means you know a formula. No, it doesn't know a formula. It did it as a series. Then it expanded the series to enough terms to approximate the answer to whatever decimal point it wants to spit out at you. So that gives a part of why series are important, one of many reasons, is because of things like that. There are going to be times when the normal way of doing calculus that you're used to, it can't work. Like you don't have the rules for it, you don't have the techniques for it. However, you can somehow use a power series to represent the thing you're talking about. Do an integral, do a derivative, do whatever you want. Usually not a derivative. Derivatives tend to be a lot easier than integrals. Do an integral or something else that's crazy, and you can get an answer in series form. Now that series might convert to something very nice, which is some other function. However, a lot of times it's not going to be something very nice. And you might say, well, now I know the answer is an infinite number of terms. How is that actually useful? Well, it's useful in the sense that you can approximate it to within any degree of accuracy you want using one of the approximation theorems. And so your calculator or whatever you're looking at can actually give you an answer to within any desired degree of accuracy. Okay, I don't really care about the answer, I just want to know the answer to 15 decimal places. We can approximate this to 15 decimal places. Right? You probably won't even take that many terms. So to actually approximate the Lagrange interval when you're plugging in this number, how many terms are you going to need before this guy is going to give you something that's less than 1 over 1 with 15 zeros to it? The denominator is growing like 9n plus 2. It shouldn't take that long. A couple hundred terms, which is nothing for a computer. Next time what we're going to do is we're going to figure out how to build power series from scratch. So everything we did in today's class is because we actually know what this guy was, right? And pretty much we just used manipulations on this series to figure out some other thing. Well, if I can force it to look like this guy, I can figure out a series for it. But what if I can't force it to look like that guy? What if my function was the sine of x? Is it possible to express sine of x as a power series? How are you going to change that guy to look like this guy? No, we'll need a way to find power series of functions, kind of building them up from scratch. And there is actually a way to do that. It is called a Taylor series expansion. And that's what we'll look at next time. And then we'll look at some other applications of that, some pretty cool, important things. So, that's all I have today. Over the Thanksgiving break, please review series. You need to build up your information on that. I'll see you guys on Monday.
Is our midterm till Tuesday?
Yeah, that's the last recitation, right?
Yeah.